So if you remember from last session, we started direct numerical simulations in turbulence modeling, and then there we said that okay, we have a spectral methods and regular finite difference methods. So we said that okay, finite difference methods are there, so we don't touch that thing. We're gonna study the spectral methods, know the basics about these spectral methods first, because they will give us uh, more reliable time in order to solve the equations with computers. And in the spectral methods, if you remember, this is a kind of review page. We said that we want to transform all the equation sets that we have in a physical space to the spectral space. And we said that mass equation, momentum equation, and other equations will be transformed to the spectral space as we have in physical space the variable like u, which is a vector velocity that is a function of both space and time. It can be expressed as a summation of wave numbers as a finite Fourier series. And our work is actually to do this transformation. Our work is to find the uh, evolution or conservation equations of the Fourier modes in a spectral space. So this time your Fourier mode will be a function of wave number and also your time. So time, for the time we said that actually if you freeze each realization, then there won't be any time at each realization. You have frozen the time there, so it's only the function of the wave numbers. The Fourier mode, which is the u hat, the vector of u hat, is only a function of wave number. And then we said that there is this summation for the transformation. So your velocity, physical velocity, is the summation of infinite number of Fourier modes, and the wave number is nothing but 2 pi times n1 over L, n2 over L, and n3 over L. And we said that these ni, n1, n2, and n3 are the number of waves along each physical uh, dimension. For example, if you have a box with side length L, we said that if you just consider the length and width of the box, so you just consider a two dimension of that box, you can somehow represent one of those many Fourier functions. I mean, not the Fourier modes like this. So if you just consider a wave traveling on a surface like on a lake or something, when you drop a stone on inside the lake, you will see these two-dimensional waves. We can have the same thing. So you will see these crests, these lines represent the crests of the waves. Mm, So you will see these waves that are traveling somehow diagonally. Uh, so you will just count the number of crests that you have. So along the x1 direction, you have four number of waves. Along the x2 direction, you have two. And since it is two-dimensional, there is no wave along x3, so it is representing actually your wave number of 420. And then if you remember, in the last session we said that in order to make the transformation simpler, we have to assume that the waves have periodic behavior, because the wave is also sinusoidal thing, so it is a periodic thing. So we actually assume that on the borders, uh, borders of our cube or our square, the waves will just repeat themselves. That's why then it won't be a function of time anymore. So it is only a function of, I mean, the physical velocity will be only the function of wave number. So now we want to do the transformation. In a spectral analysis, we define this operator. I mean, it's kind of F, let's say F operator, F subs mm, f of k, fk of u of x, and this operator, what it does, it is applied to, as you can see, it is applied to your physical vector, physical, for example, velocity, and it will give you something like this. So fk of physical velocity is the uh, uh, actually this bracket, this sign is uh, meaning the averaged over length L. So the average of what? The average of your velocity times e to the power minus I k times x. And this thing, as I said, it is the average thing over length L. And the k, as you know, it is your wave number. So the mathematical formula of this, the average is, okay, we have a cube. So the average of a cube is everything, the summation over L cube, right? You want to average it. So 1 over L cube times this summation. So this is a triple integration, means that you have to integrate along uh, all three directions, dx1, dx2, and dx3 of your velocity times e to the minus ik times x. So the result of this operator will be uk. So this f, this operator, when it is applied on u, it will give you the u velocity, but in terms of your spectral space or wave numbers. So you have such operator, and this operator you apply this operator on all the velocities inside your equations, like the momentum equation or mass equation, and you obtain the velocity in the spectral space. So this fk actually determines the coefficient of the Fourier mode of wave number k in here. So you remember that when you want to represent some periodic function as Fourier modes, you would get some coefficients for each terms inside the Fourier representation. For example, if I apply the operator, the F operator, to the momentum equation, so this is the momentum equation that we have, the physical momentum equation. In the momentum equation, in addition to velocity, uh, I have derivative of velocity, right? dv dt, it has the derivative of velocity. And you can actually show that the result of applying operator f to the velocity derivative will be like this. Okay, it's a mathematical thing. So if f of u is uk, f of derivative, I mean the special derivative of u, will be something like this. So it is just ik times u. So we don't want to actually know why it is happening, but it's a mathematical thing. You just remember, keep it in mind. What we need to understand is that the operator f is defined to transform from physical space to spectral space. That's it. That's enough for us. But for more information on this derivation, ik times u, you can refer to chapter 6 of Pope's Turbulence book. So the important result of this actually derivation is that you see that if you apply this f to the derivative, what you obtain in here is actually the derivative will be disappeared, right? There is no derivative in the right hand side of this equation, right? So the operator f is doing something that the derivative just vanishes. This is very important for us. I have only multiplication of three numbers. I have I have k, which is the wave number. I have the Fourier mode uk. Therefore, if I continue to apply this operator to uh, all the terms in momentum equation, all these terms in momentum equation, this is originally is a partial differential equation, but it will be very much simplified, and after applying operator f on this equation, you will get much simpler equation, which is just an ODE, ordinary differential equation. So the differentiation with respect to xj in physical space will correspond to only a simple multiplication by ik in wave number space. This is very important for us. So one example I'm going to give you, which is the continuity equation, for example. You know, the continuity equation for any incompressible flow is duj dxj equal to 0. And you know that j is repeating index, so it's kind of summation. You know that it's a dummy index. So I want to transform duj dxj into wave number space. I have to apply the operator f on this equation. So you see this equation. Operator f is applied on this equation. So what I will get, as we said, uh, when you apply operator f to the, uh, let's say, du I duj dxj, which is the uh, derivative of the velocity, will give us ik times u. And operator f is applied on the 0, so f of 0 will be 0. So IKU is 0, I is not 0, so KU will be 0. So this is very easy. Therefore, the continuity equation in a spectral space will be KJUJ equal to 0. Since the J is dummy index, repeating index, it means that the summation of K1U1 plus K2U2 plus K3U3 will be equal to 0. Mathematically, we can have infinite, actually, numbers of modes. So this J this time does not represent the spatial dimensions, okay, because we are in a spectral space. So we have infinite number of terms in here. You have to sum up all these terms to actually represent a fully random signal. In numerics and practical applications, we cannot have infinite number of terms. Therefore, in order to be able to replicate the physical reality of the turbulence, you have to have as many numbers of modes as needed. I'm not saying as many number of modes as possible, meaning that how high should this J number go, as high as the highest wave number in your domain. And the highest wave number actually corresponds to your Kolmogorov length scale, because the highest wave number corresponds to the smallest scales. And this is the Kolmogorov length scale. So if you have wave numbers higher than that, then it is irrelevant for you. So you would just need to cut this J at some point. This equation is a simple algebraic equation, as you can see. As K1U1, K2U2, K3U3. It is an algebraic equation, and you only need to solve this equation, not this equation, which is a differential equation. Is there any questions?
No hocam.
No.
So you can guess how we can do the same thing for momentum equation. Momentum equation involves terms like we said dui dxj involves ui times dui dxj, and etc. So also momentum has this dui dt, right? Because it is inside the momentum equation. Except for the time derivative, there will be no other derivatives in the final equation when you get the final equation. The rest of the terms will be just multiplication and summations, just like we did in continuity. So if you apply the operator term by term to the momentum equation, original, for example, original physical domain instantaneous momentum equation is duj dt plus ddxk uk uj. I can just replace these indices with anything. I just used k instead of I in here. It doesn't matter, you know it. Is equal to nu times d squared uj dxk dxk minus 1 over rho times dp dxj. So this is the physical one. This is momentum equation physical. So all the variables in here that you can see, just a second, I have to answer this call. I will. Okay, I'm sorry. Uh, where was I? Yeah, I said uh, all these variables which you see in here, uj, uk, uj, again uj, and this p, all are instantaneous distributions of either velocity or pressure. And we need to satisfy this thing at every instant of time. So let's first start with the first term, duj dt. So operator f is applied to the first term and it gives us uh, duj dt, but this time u is u hat, which is the velocity in a spectral space. So we said that only this term will be there as a differentiation, as the velocity differentiation. All other terms, as you can see, for example, you apply operator F on the second, on the pressure term. This is the pressure term. It gives you minus I times K times P hat. When you apply it to the viscous term, it gives you again another algebraic term, minus nu K squared U hat, right? So it becomes ordinary derivative. Uh, Actually, uh, when you apply the operator f on the u on the time derivative, which is partial of u partial of t, it becomes ordinary derivative. So it becomes d of u dt in the spectral space. So the nonlinear term uk uj, uh, the nonlinear term that you have will be discussed in a short. So except for the nonlinear term, we can put all the terms together and write it like this. So du hat dt plus nu k squared u hat is equal to minus ik p hat minus g. G is this nonlinear term that I just want to talk about it. So this nonlinear term is this one. Why is it nonlinear? Because you have multiplication of two velocities, right? So I will say that okay, the transformation of the nonlinear term, I will call it as g hat. And j is the number of Fourier modes, you remember, that should be relevant. So it is required to be as much as needed wave number of wave modes. So as a note, uh, I added three notes in here. The first one is that the dependent variable in this equation is u hat. And aside from time derivative, which is the first term, there is no derivative in the above equation. You see that there is no derivative. It's all ordinary algebraic equation. Fourier modes are not velocity components. See that Fourier modes are not velocity components. Don't uh, fool yourself. The maximum have three physical velocity components, but Fourier modes can be more than three, as we said. This J should take values from the largest numbers to the smallest ones that are relevant to your turbulence simulation, as I wrote in here. So, uh, what will I do next? I can decompose the G. This is what I got. J is 1, 2, 3, 2, whatever. I said that I have this G and I can decompose G, which is a vector, into two components as you see in this figure. So you have your G, you decompose it as uh, G component, which is parallel to your wave number. It is parallel to the K, and another component which is normal to this wave number. So there is a derivation which I'm going to skip, and uh, if you are interested, you can go to the Pope's book. But the only thing is that the G, the nonlinear term, it is decomposed into parallel and the normal components to the wave number. And what I'm going to do is to multiply the equation that I got by k, I mean wave number with an index k, k, and use the continuity equation. When I use, when I do this, multiply this plus continuity equation, this gives the well-known Poisson equation. Poisson equation for pressure. But of course, it will be Poisson equation for pressure in wave number space, not in a ordinary special coordinate system. So first, let me remind you the Poisson equation in physical space. It is the Poisson equation in physical space is d squared of p equal to minus d dxj of d dxk of uj uk. So this is how you relate pressure to gradients of the nonlinear component, right? In the Poisson equation, you actually have your pressure in here, and your pressure is related to the velocity components, okay? Nonlinear uh, gradients, actually gradients of the nonlinear components. The thing is, if you do this exercise, I mean this multiplication of k to this, and then use the continuity equation, you will get the transformed form of the Poisson equation in wave number space, which is this one. This is the transformed form. So you can do this. I mean, as I said, I can refer you to the Pope's book, and if you want to deal with the mathematics of this, you can go over there and see. You will just get the Poisson equation in wave number space. So you can write the equation to obtain actually p hat. So that p hat could be replaced, and if you replace this p hat in this equation with the Poisson equation that you obtained, then you will get this equation. So I'm trying to obtain some relations between g hat, as you see, and the u hat that you have. U hat, and this is g hat, g hat. So that everything is written based on one single term. So let's again consider the equation that we used before and keep in mind the rule of derivation for operator f. We said that if f is applied on any derivative, it will be I k times u hat, right? It's if it is the first derivative, it is I k times that mm, mode, Fourier mode. If it is the second derivative, then it will be I squared k squared. I squared is minus 1, so it will be minus k squared times that thing. And it goes like this. So your g hat, which is the transformation of the nonlinear term, will be ik of the transformation of the nonlinear term. And the ik, when you want to represent the f uh, applied on the uj you can actually use, uh, instead of two physical velocity multiplication, these two uj uk, their Fourier series are written in here, right? So you have the approximation of Fourier series of uj uk. I did nothing right now, but I used prime and double primes in these two, just to distinguish between those two. So the first one is for uj, the second one, which is double prime, is for uk. Nevertheless, they both are wave numbers, nothing else. So the final equation I get is g hat is equal to ik times the summation of uj k prime uk k minus k prime. Of course, there are many intermediary steps that I just skipped, and you can follow them from Pope's book again. So using the first equation that I had for the Poisson, I can replace g hat by a function of u hat, and uh, actually the Poisson equation involves the summation that actually uh, makes the equation very difficult to be solved numerically. So this is the problem that we have in DNS actually. Uh, if I want to explain it, the final form of the equation will be du hat dt. This is the time derivative plus viscous part is equal to minus k ik pressure times this summation. Actually, this summation will be uh, actually pain in the neck for us in DNS. So this is actually the time evolution equation of Fourier modes, which I wrote in here. And you have to remember that we started from conservation of momentum in physical space, and now we ended up with a time uh, evolution equation of Fourier modes in wave number space. And the PJK is the second order tensor. It is a 3 by 3 matrix. You have JK indices, and it is composed of some constants. You know that the Fourier modes has some constants, each one. And if you just look at this equation that I wrote in here, the left hand side is just one ordinary differential equation. It is ODE, okay? And it only involves u hat, the Fourier mode, corresponding to wave number k. But on the right hand side, numerically you actually you performed a very giant summation in here. It is a very giant summation. First of all, it has to be summed up over all wave numbers that are relevant in your domain, because you see this, it is summation over all wave numbers. So it has to be from the largest eddies to the smallest eddies. The second thing is that the summation term is um, actually what we called as non-local term, which I wrote it in here. It is a non-local term. So what is non-local? What is local? This is where the difficulty lies. Actually, it is a non-local term. The right-hand side involves u hat at k, as well as u at some other k, which is k minus k prime, which is the k double prime, for example. And it is non-linear because we multiply Fourier modes, and it will be non-linear. And also it is non-local, as I said. What is non-local? What is local? Uh, in physical sense, let me define non-local and local.